Okay, hello everyone. Welcome to the March A3D3 seminar. The subject of this month's seminar is multi-messenger astronomy, and I'm very pleased to introduce our speaker today. Villar is currently an assistant professor at Penn State, and she was previously a Simons Junior Fellow at Columbia University and the Flatiron Institute, and she obtained her PhD in astronomy and astrophysics from Harvard in 2020, and her bachelor's in maths and physics from MIT before then. So she's going to be talking to us today about some of the challenges, I think, in time domain astrophysics, in big data. So very welcome, Ashley, and please go ahead.
Yeah, thanks so much for having me. So I very much enjoy having talks that are interactive, which I hope is okay. So if people are allowed to interrupt and ask questions, please do so at any point and at any level. I will also apologize in advance that I am traveling right now, so I don't have my normal screen set up. So if I forward a slide and get shocked at my own slide, that's why. It's lack of presenter view. Okay, so I'm going to chat about, like Matthew said, something called time domain astrophysics. And I think about this in the context of big data. And my understanding is that this audience is familiar with machine learning techniques, but maybe not so much astrophysics, especially this subdomain. So let me just give you a few pretty slides of background. Time domain astrophysics just means that I study things that evolve on human timescales. So to astronomers, 1,000,000 years old is actually quite young, but to me, something that happens on order hours is something that's happening quickly. And so what's fun about these events is that we really do see the cosmos evolving in real time, and we try to simultaneously understand the high energy physics that we're looking at and the broader astrophysical story. So things like how is the nucleosynthetic makeup of our universe evolving over time? Those are the big questions we're trying to answer. In particular, I'm going to focus on my favorite type of transient phenomenon, which are called supernovae, where this is a cartoon gif, believe it or not, of a supernova, core collapse supernova, which is what happens when massive stars reach the end of their lives. They can no longer support their own mass, and they collapse under gravity, leading to this large explosion, which creates newly synthesized and radioactive elements that we see basically as a large bomb in the night sky. And my job as an observer is to try to collect as many photons as I can to understand the underlying physics, like I explained. Because this is a data talk, I really do want to talk about what is the data we're looking at, and why is that interesting in a more machine learning and data-driven context. So what we actually look at is we take telescopes, we look at pictures on the sky, typically with what they're called wide field surveys. So that's things like what Matthew's familiar with, the Zwicky transient facility, where we take a telescope, look at the same patch of the sky every few nights, and try to see if we see something quote unquote new, where this is a great example of something new. This is a supernova happening in a galaxy other than our own. We reduce these pictures just into kind of a count, an integral of how many photons do I see in this particular spot as a function of time. So ideally, to really understand the underlying physics, I would want to grab every single photon at every single point in time at every single wavelength. And that's what this GIF is trying to represent. And so we call that the spectrum, or a sequence, which is as a function of time. And really the physics we're trying to uncover here is that the overall shape tell us a lot about the bulk properties of the physics. So things like how much mass was in that star that exploded, what energy was the explosion. And then the little wiggles that we see are the emission and absorption lines of different elements that either have been newly synthesized in the explosion itself, or that pre-existed in the progenitor, or the star before it exploded. And so if I had all of this information, I could really tell a complete story about the underlying physics that are happening. However, it's very expensive to get a spectrum of an object in the cosmos, and the reasoning's pretty self-explanatory. You can imagine that I'm trying to collect photons in many, many different buckets as a function of wavelength. And so it's just going to take a long time for me to get enough photons so that the Poisson noise is small enough that I have a good signal to understand my spectrum. So what we do instead is we take really big buckets. So instead of saying, at this resolution, I ask questions like, well, what are all of, can you see my cursor? I'll speak as if.
Yes.
Yes, we can.
Okay, great. Okay, good. So what are all of the blue photons doing versus what are all of the red photons doing? And by making those buckets wider, I can collect more as a function of time. However, the cost is that I'm getting a lower resolution version of this kind of continuous function. But when I do that, so let's say I take big bucket, blue photons as a function of time, and I just make a plot of how many photons am I collecting versus time, I call that data product the light curve, which is self-explanatory. We're not good at naming things in astronomy. So that's really the data product that I think about. I think about these short-lived time series events that are low resolution versions of the underlying astrophysics. And as a kind of a silly aside, I get a little sloppy in my jargon. I'm always going to be talking about transient phenomenon, so things which blow up and go away for most of my talk. And if I interchange that with the word supernovae, which means specifically the explosion of a star, it's just because those are the most common type of transient phenomenon. So don't worry if I interchange the two. So I told you that at high resolution, this GIF, I can see these little wiggles of the various elements. Those wiggles have really been driving what we consider the classes of our different physics. So I want to be super clear that physics, astrophysics and physics is a continuous kind of space of possibilities. But traditionally, astronomers will take a spectrum at one point in time, and then they will kind of make these binary decisions of, do I see the signatures of hydrogen? Yes or no? Okay, based on that, I'm going to guess at what the predominant astrophysics or physics that's happening for that event. So for example, if I see hydrogen, it tells me that that star that exploded had a fluffy hydrogen envelope still, so it probably was some sort of core collapse supernova. And then I can go deeper and say, well, was that just a narrow line of hydrogen or a fat line of hydrogen? And that tells me where the hydrogen which is being ionized exists. And so I can then make a statement about, okay, from there, is this shock physics happening, or is it happening within the photosphere of the progenitor star? So there's two key points to our data here. The first is that we are classifying based on these high resolution features. I can see it with high resolution, or spectra. And then the second key point is the hierarchy that you see. Naturally, our physics has this hierarchical type of structure to it, and it's a fuzzy one. The physics is loosely correlated to our classification scheme. Not loosely, it's pretty strongly correlated to our classification scheme, but it's not necessarily exact. I also want to point out, which I don't think I show, that the universe does not create things equally. It is very much going to be an unbalanced type of training set that we typically look at, where some classes are just comically common and some are really rare. And I, in particular, really care about the rare things, which I'll tell you why in a minute. So even though I just told you that our classification scheme is built on these high resolution spectra of supernovae, I will now argue that with minimal proof, I'll say, so I guess just believe me. Normally I have a few slides of proof, but I will argue that the physics is still encoded in these lower resolution versions, or the light curves, where again, these different lines well, in this case, I think I was trying to represent different physics, but you can imagine that they're different colors of photons, the blue versus the red. And the shapes, the colors, and the brightness of these light curves that we see do actually still have strong to medium correlations with the underlying physics. And so this is really setting up the issue that we have, which is that the low resolution light curves are the cheap thing to observe, and the high resolution spectra are the expensive thing to observe. But the high resolution spectra have very exact classification of the underlying physics, where our light curves have a much fluffier and less exact classification that we can get at. Okay, this is our first non-cartoon. So this is actually the type of data that we look at, and it has some really fun properties for machine learning problems. So I can point out some silly things and not silly things. So I'll always be showing these types of light curves where I'll show as a function of time, different, the y-axis will always be some function of brightness. Comically, astronomers, we use a logarithmic scale, and it's also a negative logarithmic scale. So if you see this that appears upside down, it's not. It's just the weird way that we write down luminosities in astronomy. Okay, so now the less silly things. These different colors will always represent the different colors of photons, so where I put those large bins. Again, in theory, all of these observations are being, you can think of it as being selections, well, they're literally selections of the same two-dimensional, where the dimensions are time and wavelength, evolving function. So they all should be very highly correlated, although they shouldn't look exactly the same because we're probing different regions of that spectrum. They tend to be sparse, as in they only last for about, let's see, a few months at most. And within that time, we only get between 10 and, if it's really good, like 100 data points or observations of those. I don't say it here, but they are transient, which means that they are aperiodic for most of this. We'll be talking about things which show up, they go away, they're not periodic. They're very noisy, as you can kind of see here, and that's, again, partially because we're probing this low resolution a low resolution look at the underlying physics, and also just because they're noisy. They tend to be, we look at the dimmest things that we can look at. And then, importantly, they're multivariant and they're unevenly sampled in two different ways. The first is that, obviously, they're not sampled evenly in time. But then also, we don't get the same filter observation at the same frequency. So you can see that we have just a few samples of the green or the G band photons, and we have a lot more samples of the I band photons in yellow. So I like to probably naively compare this to, let's say, patient medical data, where someone will come in for a blood test, maybe weekly, but they're not going to get all the blood tests every single week. So that's, I think, the best way of thinking about it, where all of them, though, should somehow be correlated to the same underlying function of a patient. Oopsie. Are there any questions about the data formats that we think about for this talk? It really drives the eventual techniques that we are using as a community to solve the physical problems we're interested in. I will give it just a few seconds. Good, we're all perfect astronomers. So let's talk about numbers now. So we find lots of supernovae every year, which is very fun. So currently we find about, I say 10, it's more like 20,000 supernovae every single year, where discover means that these surveys, which are looking at the same points of the sky every few nights, they see a new star and we think it looks close enough to what we think a supernova looks like. And I showed this histogram, which is showing just the number of supernovae discovered per year as a function of year starting in the 1980s to really highlight the fact that this has been an exponential growth in our discovery rate, and it's really being driven by these the surveys that I'm describing. That's what these colored histograms are highlighting, which is not so important for our talk. The key point is the fact that it's been growing exponentially, and it's quite a large number at this point. However, This story is actually going to drastically change in just a few years. So in April of 2024, a new observatory is going to be built called the Vera Rubin Observatory in Chile, and it's a collaboration between Chile and America. And it will be this public survey that will start a 10-year survey of the southern hemisphere. So it will look at basically the entire southern hemisphere every few nights. And it's going to be really a game changer for our field of time domain astrophysics. And there's kind of two reasons. The first is just the fact that it's such a wide area, the entire southern hemisphere. And then the second is that it's at this really unprecedented depth. It can really see some of the dimmest objects that we've ever seen. It's going to produce, for a sense of scale, something like, 20 terabytes every single year. So it's quite a lot of data. And I, of course, highlight the fact that it's named after Vera Rubin herself, the discoverer of dark matter. So what's Vera Rubin going to do? Now I've switched my axis to a linear scale, but showing the same histogram, just to show off how exciting it will be. But more seriously, the Vera Rubin Observatory is going to literally break our exponential growth that we've been experiencing for the last few years. We're going to have a jump from about 10,000 discoveries every year to 1 million new supernovae every single year, which is well over 1,000 every single night. So that's what this arrow is. I've also drawn this black line, which represents now the number of supernovae which get a spectrum, just at least one spectrum, during the time that they are exploding. So remember that the spectra represent the high resolution, high confidence classification scheme that astronomers traditionally use to get our first guess or to classify the underlying physics. So right now we classify roughly 10%. It's actually a bit lower, but 10% of all supernovae we discover. And to be totally honest, we kind of throw out 90%. We just don't do much science with it. And that's fine. However, when Vera Rubin comes along, we do not expect to get notably more resources to do spectroscopic follow-up. So within a factor of several, like this absolute number of spectra that we get is not going to increase. Therefore, the relative fraction is going to, unfortunately, drastically decrease, where now we are only going to have spectra, or a traditional label, for 0.1% of all of our events. And now we're really faced at a crisis of deciding if we want to throw away 99.9% of available science, or if we want to really embrace the big data revolution that we're going to have and think about new methodologies of doing classification and also other decision making that I'll mention. In particular, I'm just telling you about fractions really, so let me continue on that. I like to really drive home this point though. So I think of it as having a new needle in the haystack problem, where we'll observe millions of supernovae every year with LSST, meaning we'll get light curves, and we'll have algorithms that at least say this looks like a supernova in some sense. Thousands of those, if I'm being generous, will get a spectroscopic classification, which means that they will get a traditional label. I'll have one guess at the underlying physics. And then just realistically, maybe 100 at most are going to get active follow-up, where I mean twofold. First is, at a practical level, multi-wavelength follow-up, which means that we trigger other resources to really get that full, what are all of the photons doing sense from radio through X-ray. But then on a human scale, just the number of human hours we need to devote to these things to do our science, understand, unpack the physics that's happening, and write up a paper, 100 per year seems reasonable, if not generous. And so, again, I'm just telling you about fractions, 100 in a million. We're talking about 1 in 10,000 level of quote-unquote importance to driving the field forward that we need to actively decide on, because these things appear and go away, and we only have a set amount of time to figure out whether or not we want to study them. And so, again, I just told you that We currently discover about 10,000 supernovae per year. So this is literally as if the community had to come together once a year and make a decision that we can only publish one. Which one will it be? I think it's a fun philosophical question of what does it mean to be one of those needles? But not one that we'll really get into, except for I will push what I think we should do. This is showing, actually this is also from the Zwicky Transient Facility, recent paper. This is showing a breakdown of just the different supernova types. And like I mentioned before, the universe does not make them equally, so there are some majority and then many minority classes. But this is really just to highlight the fact that even the most rare events that we know about today, and I'm not going to go into the physics of those, but let's say things that are like 1% of all supernovae we know about, even those, we will find 10,000 of them every single year. And so even the most absolutely rare astrophysics we know of right now is going to be a member of our haystack, not a member of our needles. And so one thing that I advocate for is that, well, it's not so ridiculous, although it's a little bit of a fishing expedition, to say that Vera Rubin Observatory will observe something really unexpected, some new sort of astrophysics that we weren't even prepared for, which I call the unknown unknowns. And I think these are very strong contenders for members of our needles that we should be looking for actively. And so with that in mind, I'm going to describe how we design our machine learning methodologies to be sensitive to anomalies or things that we don't know we're looking for. Okay. So now we're going to talk about, I'm going to go faster. I'm going to talk about our machine learning. So all of this is really going to basically be representation learning, which just means that we're going to do dimensionality reduction. We have these light curves that have anywhere from 10 to 100 data points. And from them, I want to grab interesting features that I can use for a number of tasks, which include 1, classification, so guess at what their underlying physics is, and 2, anomaly detection. So let me figure out what the unknown unknowns are. And to be one of the fun things is that we're doing this in real time. So I need something that can actively update as we get data. I won't spend too much time on this. I just want to point out the fact that if you are just a pure ML practitioner, astronomy is a very, very fun field to get involved in because our data is totally open source and we have a combination of real and then really nicely simulated data sets that you can play with. Although I will also openly admit that it's not exactly, we're not living in the land of big data right now. Our simulated data sets have order millions of supernovae and other transients you can look at. Our real data is more limited to in the thousands, which leads to other kind of interesting training problems that I won't go into detail about. Instead, I'm just going to focus on one of the solutions to the problems that I've stated, which is building an autoencoder that has all the right adjectives that help us solve this problem. And by that I mean it's actually a variational recurrent neuron-based autoencoder. And I'm happy to talk about any of them, but we're going to step through what recurrent is and what an autoencoder is together. I want to point out the fact that this is a semi-supervised method I'm talking about. I don't highlight it too much, but the first step we're going to take is to be completely unsupervised and just ask the question, can we build a data-driven latent representation space of our supernova light curve data sets, which is meaningful in some way that's helpful to us? And for that, we don't need to know the underlying physics at all. We're just asking a data clustering problem, kind of. And then the supervised learning happens when we're asking specifically classification style questions like, can I actually go out and find the core collapse supernovae from the thermonuclear? If people haven't seen an autoencoder, it's unclear to me if we all have. I'll go medium paced. So an autoencoder is just an architecture of a neural network where it has 2 key features. One is that you are going to, in your objective or cost function, you are going to try to, as best you can, recreate the data that you feed in. So in my case, I'm going to give it these beautiful light curves, and I'm going to ask it to return that light curve to me. That seems pretty silly at first. If I multiply this by 1, I've accomplished my task perfectly. So the second key feature of an autoencoder is the fact that it has to perform some dimensionality reduction. I don't just want to multiply by 1. I want to learn something. And so this just happens by a series of really any layer type you want. It can be the most vanilla, just like fully connected layers, and they decrease in size until they reach some minimum, which should be a small number of neurons. And that number of neurons should be able to fully represent the diversity of your data set that you're showing the autoencoder. And so in a physics talk, I normally use the analogy that this is just like how we learn. This is really similar to us fitting a physical model. I can write down an equation which describes this light curve, where the free parameters are things like the energy of the supernova and how much mass the star that exploded had. And sure, a lot of information goes into the writing of that formula, but after I've written that, I can describe any supernova light curve with just 2 free parameters. That's exactly what's happening. Our neural network is going to, during training time, it will tune all of these various neurons, but all of the diversity should be captured by these kind of model vector, which would describe things like the mass of the star and the energy of the star. To be very clear, I'm not actually going to say that this is interpretable. It's not. I have actually purposely not told my autoencoder about the underlying physics because I wanted to be physics agnostic. I wanted to understand that, it should be sensitive to unknown unknowns. And so by definition, I shouldn't feed in every piece of physical knowledge that I have because it's likely incomplete. So that's how an autoencoder works. Very happy to answer any questions on that. I hope, okay, good, there aren't any. The recurrent adjective is just describing the types of neurons that I have, where I think people are familiar at this point with recurrent neurons, but please let me know if you're not. The idea is just that, it's constructed such that the neurons will have a memory of the previous data you've shown. And so the idea here in this example is that as I get more observations of my light curve, every time my autoencoder is going to try its very best to condense this light curve into just a few numbers. We're saying 10 in this case. But the more and more data it has, the better and better it'll do at guessing the underlying full shape of the light curve, where we have constructed this architecture such that I actually am calling, it's almost like I'm calling a function at any point in time so that I can fully reconstruct a light curve with these 10, this isn't 10, but whatever, these 10 free parameters and a time. And so let me show that in real life really quick. So this is a real example now where, again, it's just showing a light curve, which is time versus some brightness. The points are real observations in the different colored photon bins, and the lines are the autoencoder's decoder reconstruction. So what happens is that I've done all the training. We're in test time. I tell it about all these photons, which are currently visible, and I say, okay, with that information, please try your very best to decode what you think the remainder of the light curve will look like. And this is its best guess. So because of the architecture we've chosen, we're able to interpolate and extrapolate. To be honest, it's not doing a great job. This is not exactly what this type of supernova should look like. However, what's exciting is that with just a little bit more information, so there's a few new points here, it is getting much closer to the real light curve shape that I expect for a type 1a. I'll just skip ahead for that. And so when it has finally the remainder, it's not a perfect fit to my light curve, but it's a reasonable estimate of the remainder of the light curve given the data. So that is to say, seemingly, our latent space has learned what, in general, supernova light curves should look like, and it's able to reconstruct those from the latent space alone. So I'm not really even going to show so many results, just instead highlight the fact that, like I said, now we've been using these latent spaces to help us do a number of tasks, mainly classification. So taking large sets of supernova light curves, which unfortunately did not get a spectrum in real time, and then attempting to guess at the underlying physics using this, using the latent space that we've learned, by putting it through something like a random forest classifier with the labeled data set we have. And we've done this for a few large data sets now that I'm happy to talk about. But we don't do anything. We typically train all of our data sets independently. There's not really transfer learning or anything necessarily happening.
So can I ask a question?
Of course, yeah.
Yeah, so very interesting. I'm learning a lot. I'm a computer engineer, right? So
okay,
fascinating. And so can we treat the encoding as a lossy compression process?
Yeah. It's okay, literally, yeah. I think these are all a similar way of thinking about the problem. It's a dimensionality reduction. And I think one thing I should highlight is that it's a nonlinear dimensionality reduction. So it's not like principal component analysis. It's in theory more flexible.
Right. So I would just think there's a trade-off, right? So the more you compress, of course, it can be trained faster. However, it becomes lossier, right? So there should be a balance between the quality and the training time, and right? How do you really achieve that?
That's a really great question. And so that's I don't know why I'm going. So the number of neurons that I put in each layer, so how many boxes instead of a 1 by 10, why isn't this a 1 by 5 or 1 by 11, where exactly it's the trade-off you're mentioning. I can miss out on diversity if I make it too small, or I can, you just end up having actually overfitting problems if you make it too big. So there's definitely a sweet spot. And so that's called hyperparameter tuning. So basically we do a grid search, like we just train lots of versions of this and we figure out which one is the Goldilocks zone of nicely reproducing our test set and not being overfit to the training set.
That's right. Yeah. Okay, so then for this data you have, how long does it take to train?
So we have tiny data sets in astronomy. We only have, I guess it depends. I'm sorry, I should say it depends. So it takes less than a day. I should just say that. At most, with our simulated data sets, we have millions of light curves, and that is still order 48 hours because each of those light curves only contains at most like 100 data points. And then for real data sets, it's in the thousands, and so that takes, honestly, hours to train. It's really not so bad.
Got it. Yeah, thanks.
Yeah. Okay. Any other questions? Oh, no. The time. Okay. So I like to take a step back and just point out the fact, again, that all of these decisions, the adjectives, as I say, of our architecture were chosen with a purpose for our science. It's semi-supervised. I guess I didn't mention this. Because our labeled training set is quite tiny. It's 10% of our full training set. And so we want to be sure to somehow incorporate knowledge that definitely exists within the data, even if we don't have those classification labels. So this is why it's semi-supervised. The autoencoder, I briefly mentioned this, it's a non-linear dimensionality reduction. We just, for physical reasons, expect non-linear transformations in our light curves, and I can go over what I mean by that. A different way of saying it, it's more flexible than something like principal component analysis, like I said. The recurrent neurons, they let us update our encoding in real time. And then kind of the last fun thing is that we can use, because this is a physics agnostic data-driven method, we can really use this to hunt for those unknown unknowns I mentioned. And so it's actually not so hard to do. It's like one line in Python to do it. So the idea is that, okay, now I have my whole bin of supernovae. I've turned all of their light curves into these tiny same-sized vectors. And so now I've created a low-dimensional latent space where I can plot, just think of it as plotting, all of the supernovae I have. And one of the questions I'm basically going to ask is, do any of these supernovae in this latent space I've learned stand out as outliers? And that process of looking for those is called out-of-distribution anomaly detection. And our hope is that the ones that stick out in this space are actually physically interesting. And I don't honestly remember if I proved that to you, but luckily they are, which is great. It's not guaranteed that to be true. And so, actually just remind myself. Okay, great. To do this, we just use something called an isolation forest. And the way an isolation, do I show? No, I don't. Okay. So the way an isolation forest works is, like the forest suggests, it's just a series of decision trees that make simple cuts in this space. So for example, I draw a vertical line here. And in doing that, I have isolated these two guys immediately. So if it only takes me one cut to isolate these, they must be pretty weird looking. Whereas to isolate some guy that's in this blob, I would need so many cuts. And so an isolation forest makes those cuts, and then it says that the number of cuts it took to make, the number of trees it took to isolate you, is inversely correlated to how weird you look, so whether or not you are an anomaly. So that's how we've been using, that's how we've been looking for anomalies in these learned latent spaces, is that we score everything with an isolation forest. We give it some anomaly number, and then we rank those numbers to figure out which are the most anomalous. I really didn't mention this. The variational adjective of our autoencoder, it just helps. It does a few things, but one of the things it does is it helps. So literally, all it is a regularization term gets added to try to make all of these supernovae, to the best of the autoencoder's ability, look like a Gaussian, just squished into a normal distribution. If you can't be squished into that distribution, it's easier to pick out the fact that you must look weird. And so that's what the variational part does. It's a little bit more of a probabilistic autoencoder. So then this is how it would work in reality, where this is a simulated data set. But we ran this on a big simulation of the Vera-Rubin data, and the thing we were interested in was understanding how it performs in real time. So this, for example, is a light curve of a really rare type of supernova called a superluminous supernova. So again, time, luminosity. This is a plot showing what the different values in that learned latent space are doing. And so this is supposed to show that they're loosely converging fairly quickly to their final values. And the color in particular shows you where it switches from being not in the top 1% of most anomalous to the top 1% of most anomalous. In other words, when it gets flagged in our system as being an anomaly, and we should trigger our telescope. And one of the exciting things that we found, although I'm not going to show it, is that for really rare phenomena, we are able to identify them as anomalous way before they reach maximum light, which is just an important number for astronomers. There's lots of fun physics that happens before they reach maximum light, and it also helps optimize resource allocation. So this was exciting. We are able to identify these things real time and early enough that we can actually kind of trigger on them and do full multi-wavelength studies. And then I will just, as an aside, mention that we do have, of course, false positives, so things which aren't exciting that were triggered, and normally for data artifacts. But luckily, those actually kind of strangely get those in our system we find get triggered after maximum light. So they're things that we probably wouldn't have triggered on anyways because we've missed our golden opportunity to start following them up. So that was really fun. And this is just showing one more view of what's happening where I'm showing you the cloud of all the supernovae again. And then this particular object, you're watching its encoding evolve as a function of time, where darker is like later in observations. And so you can kind of understand that, oh yeah, this gets more anomalous because it starts walking away from the main part of the distribution. So it's fun to see that happen in real time. Okay, that really ends highlighting of this autoencoder architecture that we've been using to solve these types of problems. Are there any questions on this section?
I wonder how the scatter plot, the third scatter plot looks like when you consider some of the other 8 features of the latent space instead of first and the second.
Yeah, that's a really good question. So I guess I'll say 2 things. The first is that
it was a great presentation, by the way. Sorry, okay. I should have started from there.
No, that's fine. Sorry, I was thinking about how to best respond to this. I think 2 things. The first is that because of this variational thing, it's the neural net's goal is to try to make this scatter plot in every dimension look like a diagonal, normal, multivariate Gaussian. Like that's its job. It clearly didn't do the best job with this space. We can see there are some correlations that exist. But most of the cuts should look like some Gaussian. But then I want to also mention the fact that, and this shows it, that doesn't always happen. And so there are really interesting features that can happen in some of these latent cuts. Yeah. And sometimes I kind of mentioned this, especially if your latent dimension is too large, you can find that some of them are even just useless. They collapse on 0, for example, with no scatter.
Yeah, I was going to say that exactly. Also, if you consider the other 8 as well for the classification, do you use them all, the 10 of them, or just the first 2?
Yeah, thank you for asking. Yes, I do. The isolation force is happening in 10 dimensions. Yeah, it is.
Great.
Yeah. Good. Any other questions or comments? Also, if things aren't clear, please let me know. I didn't know what level to assume, but I'm so happy to answer any level of question. Okay. I will admit this next part is a whirlwind of ideas, so strap in. What I've been thinking about a lot more recently that I really like bringing up with exactly these sorts of groups, which bring together domain experts and real machine learning practitioners, is understanding how do we build more interpretable, specifically I care a lot about representation learning. So a different way of saying this is I was actually very specific to say, I'm not calling this physics. This dimension is not mass and this dimension is not energy. No claim of that. But I think increasingly we do want that to be true. And there's many examples of why we would want this to be true. One of the ones that I'm getting interested in is really understanding how we can do simulation-based or likelihood-free inference. So really turning these probabilistic latent spaces into a Bayesian posterior with some understanding of the uncertainty and bypassing our really expensive sampling methods that are taking way too long to solve some of our physical problems. So I've been thinking a lot more about where exactly can we put our physics in our models. And I do want to point out that I unfortunately was not the first to think of this triangle. As I was thinking about this, I found a nice review that uses slightly different wording. I think of it in the 3 locations one could put it in when building a neural network architecture. And I'll kind of step through those one by one. Oopsie. The first is you can put your understanding of the physics in the data itself, which is to say, as one example, I keep saying this, the universe does not make our physics equally, and so we know that there's an unbalanced data set. And one thing that we absolutely do is we take advantage of this. We understand that the majority class is the majority class, and we show our neural network an accurate representation of the class breakdowns it should expect. And so you can think of this as an implicit prior on the different physics we have. One thing that happens in this kind of the story I just told you with the autoencoder is that in the case of not a lot of data, like it's just seen one data point of observations and I'm telling it, get my encoding for that supernova, which is kind of saying, guess what the physics is, it will default to the majority class because I've showed it, the majority of what I've shown in the training set is the majority class. And that's actually what I want. If my neural network called everything on the sky type 1A supernova, it would be right 70% of the time. And so I want to include those types of biases in my training. Something else that's gaining traction, though, is also this idea of including known symmetries or equivariances within your data set. And by that, I just mean something like, pretend my problem was, can you tell me whether or not this is a picture of a galaxy or a dog? And I want my neural network to understand that if I turn that picture of a galaxy upside down, it's still a galaxy. And so that's just a simple example of a rotational symmetry that must exist within my data. And again, that's something you can indirectly tell your neural network by just augmenting your data set. And that's including, in a sense, an implicit prior that is a symmetry that should exist. So that's the most common way of doing this. But increasingly, I think people are thinking about more unique ways to include this. So the next kind of part of the triangle is in my objective function or my cost function. So the thing telling my neural network how well it's doing. And one of the things I've been thinking about most recently is something I mentioned earlier, which is the fact that in our case, we know that our physics is hierarchically distributed. And so in theory, classification schemes, for example, should also have kind of this hierarchical structure to them. And there was this really nice recent work, I think I cite it, okay, it's behind your faces, I have to look, that pointed out how one would do this by just building up conditional probabilities on different subtypes. And then, so what I've been thinking about is really just how do we treat this picture like a graph as it is, and then just being careful about writing down the adjacency matrix so that we can calculate our objective functions really quickly. Oopsie. This is a deep dive for a few slides, sorry. So this is a really different physics example that I've been lucky enough to think about with a really wonderful student, Jiwan Park, and Matthew Graham's also been a part of this. So not supernovae. There's something else in the universe called an active galactic nuclei, or active galactic nucleus, which is when a supermassive black hole is actively accreting stuff. The main point is that in the same way, we still see a light curve, so just think of it as a brightness over time. The difference, though, is that when stars die, they obviously go away. They happen for a small amount of time. The black hole doesn't go away, but instead we see this kind of continuous variability. And there's a lot of theories that the variability should correlate in some way to fundamental underlying physical properties of that black hole and the system. So things like how massive is that black hole? However, we haven't been incredibly successful at detangling these complicated correlations that should exist. In particular, and Matthew's really the expert in the room on this, but people are really have been using something called Gaussian processes to understand these light curves, and then they choose a special kernel function, a damped random walk, and then they use the properties of that kernel to then predict the black hole properties. The issue with this is that this is not a damped random walk process. We don't fully understand what it is. We do think it's a stochastic process, but definitely something more complicated is happening. So one thing that I recently did with this wonderful student, Jiwan Park, is to build, I will not go into the details of this. It's called a Bayesian attentive neural process. the point I actually want to highlight in this is that it's very similar to an autoencoder. You could just think of it as an autoencoder, but one of the really interesting things we found was that if you tell your neural network to simultaneously reconstruct the AGN light curve and predict the physical properties, it actually works as a regularization of that latent space, and it becomes easier to interpret that latent space. And in this particular work, that's exactly what we did, where these are the simulated light curves of AGN, which we think will be observed. Well, sorry, there's going to be, I think, literally 50 million of them observed with LSST. And then on the right, I'm showing what comes out of our neural network, which is a guess at what the posteriors of the different black hole properties actually are. And the gray is showing you the implicit prior, so like all of the examples that we showed to the neural network to train it. So the key point here is that you can add some of your physics as a regularization term to help, you can add it to your objective function, and it does seem to regularize your latent space to make it a little bit more interpretable. And then finally, I want to highlight another project with a student in the last point of the triangle, which is that you can inject your physics into the architecture itself. In particular, one thing I like to think about are, again, these ideas of symmetries that we should know about. So in this really simple example, we were looking at periodic variable stars, and we know that the latent representation should be what's the word I'm trying to think of? Invariant to how should I say this? It should be invariant to these kind of periodic variability that we expect. So it should be invariant to phase. And so to help enforce this, we showed the neural network just a version that had padding on it. And this is something that has been previously done in the field. Josh Bloom has done something similar for variable stars. And I will also note that there's been a lot of work on building equivariances directly into neural network architectures, way beyond my understanding. I think, I forget what they're called, but there's a lot of group theory that can be directly injected into these architectures to exactly enforce equivariances that you know about in your data sets. I'm going to skip this slide. Okay. I think I just want to finish with the fact, again, as a kind of a call to any practitioners in the audience. There's so many fun methodology questions right now in the field of time domain astrophysics, where I hope I've convinced you that, even the simple problems of classification and anomaly detection are hard, but then there's a world of problems under that, having these probabilistic labels, doing fun hierarchical studies, capitalizing on really different types of data sets, combining time series with images. There's a ton of fun stuff that one can do. I also want to apologize that this doesn't sound like it was about multi-messenger at all. I do promise that multi-messenger has a large stake here. We, as part of time domain, we do follow-up events that we watch both in electromagnetic signatures and gravitational waves, and that's a whole other world of really fun problems we can address. So with that, I'll leave this here for now and take any questions. Thank you.
Thanks very much, Ashley. Great talk. Okay, we've got time for a few questions. I see David Shoemaker has his hand up first of all. David?
Greetings. It was a really good talk. And I may be just checking whether or not I've understood what you're talking about in physical regularization. Okay.
Yeah.
I think it's an intriguing, I find the black box business rather disturbing, the fact that you end up with a good fit, but you don't know what it means. And so the idea of trying to fit things into a physical model really appeals to me. On the other hand, is there a chance that in that process, you lose the opportunity to find things which don't fit your physical models, which of course is some of the most exciting stuff that you want to do. Your supernova tree's got these two different branches, and but you want another branch out to the other side that says GR is violated, or it's not a fusion explosion after all, something like that.
Yeah, I really love that question. So I will say that the anomaly detection kind of project I showed you attempted to answer this question, but it doesn't all the way. That requires that physically this looks really different, or else we won't be sensitive to it. Whereas the question you're asking is, well, what if we kind of fit models to everything and then something looked wildly incorrect or didn't fit the model itself? And I think that's a really interesting way of looking for anomalies or new physics. A problem is that our traditional way of fitting models to data requires these kind of traditional Bayesian methods with these samplers that can be really expensive. And so one thing I'm really interested in is, for what I mentioned before, this likelihood-free inference to try to get physical estimates in real time, and then asking the same questions of, well, does this stand out in my physical latent space that I know is exactly interpretable? Yeah.
Mm-hmm. Okay, good. It sounds like you're on the problem, and I look forward to the results.
If I have time, yeah. Yeah.
Bill?
Hi, yeah, thanks for a great talk. Kind of a related question. So whenever I kind of do anomaly detection, I always find that I just end up discovering a bunch of like detector glitches and kind of things like this. And I was wondering how you go about kind of avoiding or finding anomalies that you already know are anomalies and you're not interested in.
That's a really good question. And I will say, so at some level, I don't quite know why we weren't sensitive to those. I very briefly mentioned this. In the project I showed, it was simulated data, so I knew everything about everything. And in that case, we do have exactly what you're mentioning, like not interesting anomalies. Something got messed up. In particular, for us, one of the really bad ones is the distance was estimated incorrectly. For whatever reason, it just turns out that we flag those as anomalous later. So I didn't deeply explore why that happens, but that was like a lucky break for us. However, when we then applied this to real data, it found really funny events, but they were comically things that were not interesting, but hadn't been highlighted yet by a human as not interesting. So things, for example, in our supernova piles that weren't all supernovae, but I don't know how they got there. But they have largely been insensitive to kind of like absolute failures. And part of that is this variational autoencoder helps in that you get uncertainties on your encoding, which translates into uncertainties on your anomaly score. And so we can at least make really healthy cuts on if this anomaly score is really uncertain, we're not wasting our precious time looking at these events. And that helped us a lot in the purity of those anomalous samples.
I see. So you're using the uncertainty on the variational space. That makes sense. Okay, thank you.
So in this sense, the way we did it actually is that we used the uncertainty in the how do I say this? We did the isolation force in the latent space, and then we like sampled from that probability distribution in the latent space, so it translated into it. No, yeah, yeah, that's how we did it.
I completely understand. Yeah.
Can I just ground this question in like maybe more technical astronomy? Like,
yeah,
when you're looking at adding in your data set, when you're looking at your data set, do you have in like a bunch of like poor subtractions or cosmic rays that resulted in what appear to be transient detections, but aren't?
Thank you so much.
When I think about like glitches like that, that's the kind of thing where it's like, this is junk. Clearly, we don't want this. Is this going to like go out and be its own area of latent space, or is it going to get confused with other things?
Yeah, thank you so much for that. So I am 100% building on the shoulders of giants, and I am assuming that other machine learning methodologies can distinguish supernova from not supernova, or actually from bogus and real. I think that's fair because those have been developed for like decades now, and they're quite good. So the data sets I test on are all true supernovae. So I would very likely be sensitive to things like a cosmic ray not cosmic, that's actually too short, but if a dwarf nova got through, I might trigger on that. And in fact, that's what we found when we tested this on real data. It would trigger on things which were not supernovae, but just kind of somehow made it through our human inspections. I hope that answers your question. Yeah. There's
definitely
so
does.
many
I
people
mean,
working on this problem, and I'm 100% piggybacking on hoping that theirs are working excellently, because I think they are.
yeah, I mean, I'm just thinking like last week we had an event at like 5 megaparsecs. We were like, oh, this is really exciting. It got
Yeah.
reported. It
I
had
know
a
exactly.
really high like real bogus
Yeah.
score, so like that
Yeah.
was not necessarily a great thing, but it also was like not a supernova, so we didn't
No,
care.
yeah.
But it was a real event that
Yeah.
still appeared to the pipeline as potentially a high probability of being bogus. So
Yeah.
I understand that. Like, I really hope we have this solved in the next couple of years.
Yeah.
But
Yeah, and I know exactly what event you mean. That's funny.
Eric, next, please.
Hi, Ashley, and thank you. I really enjoy your presentation. Now, is there any standard set over which, let's say, if I have my own variational autoencoder, then I want to give it a try? Is there any standard set of light curves where I can give it a try, or when you compare with method A versus method B, has there been any attempt to standardize a reference data set, which actually, beyond physics, especially in electrical engineering and computer science, it has been more or less the standard over the years as we're trying to,
Yeah.
fine tune and get the ultimate method for, let's say, image extraction or edge extraction. And this actually segues to many things that folks have asked earlier, namely, if is there any transportability of the code? Now, of course, when you're talking about artifacts, maybe not. Maybe cosmic rays are not falling equally necessarily to all. But if you take your ZTF algorithm, can you apply more or less as is to the Vera Rubin?
Yeah.
And of course, this goes back to if there is some standard metric and data set that maybe it can become, or maybe it is already available and it can be used in the broader community.
Yeah, that's a very good series of questions. I'll try my best to answer. So on the standard data set, this was a huge problem for a while. And again, I want to highlight the diversity was the issue. Is there's so much that can happen in our transient sky that no one team could realistically simulate all of it. And finally, a wonderful group came together and did. Those leaders were Renee Holchek, Rick Kessler, Gotham Ryan, and a whole bunch of other people. They made a cackle competition for something called the plastic simulation. And it's 3 years of, as best of our knowledge, everything that can happen in the transient universe, including like variable stars, tidal disruption events, kilinovae. They ask the community, give us your models, we will simulate it to the best of our ability. So that's kind of now the gold standard. They're going to come out with a new data set called Elastic, which will be the new gold standard, I'm sure. Okay, so that's on data sets. And we do compare now to that with a huge caveat that that simulation it's not the full systematics that we expect in a real survey. And so we have found that, there are differences. If you train something to work really well on the simulated data set, it doesn't quite cross over to reality. So now thinking though about one algorithm, and you want to just do a domain transfer, like I trained on ZTF and now I want to test on LSST, it's really hard to do that. And the reason why is because absolutely these algorithms are understanding something about the data, and the data properties of these surveys are just so different that it's hard to do that transfer without some form of transfer learning.
I see.
Yeah.
Thank you.
Okay, Dylan?
Hi, yeah. So my question is kind of related to maybe the first two. I'm curious whether or not, because indeed this sort of problem of dealing with like detector glitches and stuff like that, I think is something that happens with everybody. I wonder if these sort of parameter estimation regularization techniques are useful at all in combating that, and whether you've tried these ones that you made, these networks that you made with that sort of, with that technique, and seeing that it changes how this happens or not at all, maybe.
Yeah, I understand what you're saying. I have not. So again, like I've only tested this on clean-ish data sets that I think are predominantly supernovae. I do think I don't know on top of my head if you would necessarily benefit from having physically interpretable latent spaces, because in either case, you would hope that like a dead pixel clusters in a specific way in my latent space, whether or not it's interpretable or not. One thing that's nice about the physical ones is that they're guaranteed to be continuous. So like my dead pixel won't appear over here and over here in the latent space, which is confusing. They'll be clustered together. But the variational autoencoder kind of also guarantees that. And so it's honestly unclear to me. Yeah, but it's a really good idea. I like it a lot.
Okay. Yeah. Thanks.
Yeah.
Great. Okay. Well, we're at 10 past the hour.
Sorry.
So, no. This has been great. I just want to say thank you again to Ashley, and thank you. And Phil, I think you can end the recording now.